Okay, so okay, so I think last time in previous weeks you have learned about Fourier transform, no? Fourier analysis or Fourier transform, discrete time Fourier transform actually speaking. Okay, so and I think in signal and system 2, signal and system subject, you have learned about Laplace transform also, no? Laplace transform. So basically, I think already you have learned these two type of transformation. Okay, these two type of transformation. I think you can remember that in Fourier transform or Fourier analysis, we are going to transform time domain signal. So actually, we are talking about signals. Okay, we are talking about signals, and our signals are normally voltage or current or power signals. Okay, we are mainly focusing on this type of signals. Okay, and most probably we like to represent our signal in time domain. Okay, so it is a normal practice way. Okay, to represent a signal in a time domain. Okay, so we are using different transformation techniques. Okay, to convert this time domain into different domain. Okay, actually this transformations are not strictly to time domain signals. Okay, they can be used for other domain signals also, but we are speaking about time domain signal. Okay, so I use the word time domain signals. Okay, it is not 100% correct, but for our content, that is the case. Okay, time domain signal. Okay, so in Fourier transform, I think you can remember that because you have learned it in last previous week. Okay, you convert a time domain signal into frequency domain signal. Okay, into a frequency domain. Okay, I think if you can remember the Laplace transform also, you convert time domain signal into X domain, S domain, into S domain. Okay, so this S is a complex variable. Okay, this X is a complex variable. Okay. So today also we are going to learn about another transformation. Okay, that is a transform. So it is a brand new topic. Okay, so our topic is a transformation, transform, and its application. Okay, its application. Okay, okay, I have uploaded the note to the LMS today. Actually, that is given by Dr. Udesh. Okay, so I have uploaded it to the system. I think if you can download that note. Okay, let's see. So So I think this is the link, no? This is your LMS page. Am I right? I have uploaded the note to this one. Okay. I think it is okay. So this is your page, no? This is your LMS page, no? For this course for digital signal processing. Am I right? So I have uploaded the note. Okay. So actually that note is directly extracted from your textbook, okay, from your reference textbook, that is Perkins DSP book, okay. So that is the third chapter of that book, okay. So you can, if you have that textbook also, this is the third chapter, okay. So so we can use this as our note, okay, for this topic, okay. 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 So we will continue. Okay. I hope you can download the note from the LMS. Okay. So so our topic is a transformation and its application. Okay. Uh, so actually, is a transformation is discrete time version of the Laplace transformation. So if you can remember that, we use Laplace transform. Okay, we use Laplace transform for continuous time signal. No, we use Laplace transform for continuous time signal. Okay, and for discrete time signal, we use is a transform. Okay, so we can say that this is a transform. Is a transform is the uh, discrete version of discrete time version of Laplace transform. Okay, Laplace transform. Okay, so many properties and many concepts are uh, basically equipped with this Laplace transform. There are some equalities as well as some different also there. Okay, so we will see gradually what is this is a transform and how we can apply them to study or analyzing uh, some system. Okay, normally we used these transformation techniques. Okay, these all transformation techniques we normally use to analyze and also for designing system. Okay, actually linear time invariant system. Most probably these transformation techniques are used to analyze and designing a linear time invariant system. Okay, systems. So we will see how we can analyze and design LTI system using Z transform. Okay, before that we have to get the idea of how we perform the Z transformation and how we perform the inverse Z transformation. Inverse Z transform. Okay, so we will see. So I will directly give the formal equation for Z transform. Okay, so this is the formal equation for Z transform. Okay, so that is see, so I said that this is for discrete time signal. Okay, I already told that this is for discrete time signal. Okay, so you can see that the Fourier transform we are using continuous time as well as discrete time signal also. Okay, but Laplace transform we are using only for continuous time signal. Continuous time signal. This is continuous time and this is discrete time signal. Okay, and Z transform is strictly used for um, discrete time signal. Okay, discrete time signal. Okay, so you know that normally discrete time signal we represent using number of sample, using sample number, not time. Okay, using as in xn. Okay, so this is sample number. Okay, this is sample number, and I think you already know that this n is always related with time. Okay, this n is related with time. uh, so if you can remember that, I think I have explained this in a MATLAB session also, because this concept we need to do the sampling things. Okay, this knowledge we need to do the sampling. Okay, the relationship between this n and the time. Okay, so it is related with time, uh, with sampling time. Okay, if the sampling time is t naught, n t naught is equal to t. Okay, so this is the relationship between the n number of samples and the time. Okay, and this t naught is nothing but sampling time. Okay, sampling period, or 1 by f naught, 1 by sampling frequency, 1 by 1 divided by sampling frequency. Okay, I think these things you already know. Okay, so we can continue without a problem. Okay, so this n is a sample number, and it always please keep remember that it always show us a time value. Okay, okay, it's always corresponding to a time value. Okay, so this is also a time domain signal. That is what I want to tell you. Although we represent this using n, okay, so this n is always related with the time. Okay, so this is a time signal, time function. Okay, more correctly speak, it is a time series. Okay, this is a time series. Okay, that is the idea you should have. Okay, so this is the sample number, and then is an integer value. I think you already know that n is integer value, and it can be 0, 1, 2, 3 up to infinity, or -1, -2, -3, like up to infinity, minus infinity. Okay, so these are plus samples and these are minus samples. Okay, so the samples can be plus or minus. Okay, if we refer the sample as a zeroth sample, so the right hand side of this the right hand side samples are referred as plus sample, and the left hand side samples are referred as minus sample. Okay, so I think you know this already. Okay, uh, so if we have a time series, if you have a time series called xn, okay, if you get the Z transform of this xn, so this is a time series, time signal, time domain signal. Okay, if we get the Z transform, this is it is donated like this, Z of xn. Okay, so if we get the Z transform, the so it denoted using capital X Z. Okay, so now it is in Z domain. Okay, so I think same notation we are using, we have used for the Fourier transform. No, in Fourier transform also we have used the same representation. If we have xn, okay, if we get the Fourier transform of xn, so it will be capital X omega. Okay, so in the same manner, we can define or we can denote the Z transform. Okay, Z transform also. Okay, so it will be XZ. Okay, so XZ will be n from minus infinity to plus infinity. Xn Z minus n. Okay, so this is the definition for Z transform. Okay, so this is the definition for Z transform. Okay, this is the definition for Z transform. Okay, and you can see that this Xn is a time series, time domain signal, time domain is discrete time time domain discrete time signal. Okay, and now we have converted it to the Z domain. Z domain. Okay, so this is the formal expression for Z transformation. Okay, and also there is a formal expression for the inverse Z transform. Okay, inverse Z transform. Okay, so all these things are included in your note. Okay, so after you get the idea, you can refer the note. Then I think you can get a better idea about this. Okay, so inverse transform is so you know that if we have a Z transform series, okay, if we get the inverse Z transform of this X Z, we will get our time series again, Xn again, time domain signal again. So the definition is we have to do an integration to 5j. Okay, we have to do the integration, and it is a closed loop integration with the this C is actually the limit. Okay, we call this contour of integration. Okay, integration. Okay, and we have to do this integration x z n minus 1. Okay, with respect to dz. Okay, so this is the inverse is a transformation formula, is a transform formula. Okay, so actually this is somewhat complex. Okay, because we need to understand the complex variable theory. Okay, otherwise it is hard to perform this kind of integration. Okay, so I think in your mathematical module you have learned this contour integration things. Okay, so anyway, in this course we are mainly focusing on Z transformation, not inverse Z transformation. Okay, not inverse Z transformation. We are mainly focusing on Z transformation. Okay, so do anyone have idea why we are mainly focusing on this Z transformation? Actually, it has a practical sense because in practice we normally have time series, no? Okay, if we get a signal, okay, if we generate a signal, okay, in practically, if we generate a signal, for example, if someone talk to a microphone, okay, it will generate a voltage signal. Okay, this is a acoustic signal, no, audio signal. Okay, and that is a time domain signal. Okay. And if we get if we sample this, okay, if we sample this, we will get a discrete signal like this, discrete series, time series like this. Okay, and we have this time series. Okay, in practice, first we have this time series. Okay, in practice we can get this time series. Okay, but when we are sending this to some kind of system, say to a filter, okay, if we send this sample signal to filter for processing, okay, then if you use the Z transformation, this analysis will be easy. Okay, so sometime we may prefer to convert this time domain signal into Z transform. Okay. Okay, did you get it? Okay, so we have to perform the Z transform process. Okay, we have to perform the Z transform to convert this time domain signal, time series, into Z domain, Z domain. Okay, but we have originally we have this time series. Okay, so there is no need for inverse conversion. Inverse conversion. Okay, there is no need for inverse conversion. Only we perform the Z transform, it is enough. Okay, so in most probably in practical application, we have to convert the Z transform. We have to convert the time series into Z transform, but we no need to do the transformation back. Okay, but when you are using Fourier transform, that is not that case. Okay, in some system, we have frequency domain signal. Okay, for example, if you consider OFDM system, okay, if you do this multiplexing using the orthogonal frequency component, okay, so this is a frequency domain. This is the frequency domain type. Okay, then if we want to, so normally we prefer to have a signal in time domain when we are doing the transmitting or other things. Okay, because the analytical is somewhat sometime at that point the analytical may be easy if the signal is in time domain. So sometimes we have to convert this frequency domain into time domain signal. So you have to use the inverse FFT. Okay, so I think if you have look at OFDM system, there is a block diagram to perform this minus the inverse FFT inverse FFT algorithms. Okay, so I think in Z transformation, that inverse transformation is not very much used. Okay, we normally use Z transformation, but we are very rarely we are very rarely using the inverse Z transformation. Okay, so mainly we are focusing on this Z transformation stuff. Okay, not inverse Z transformation stuff, but you can remember that there is a formal way to convert Z transformed signal into time series circuit. Okay, okay. So we have this uh, identity xz is equal to sigma minus infinity to plus infinity xn z minus n. So we have this identity. Okay. So to get clear understanding, we will do one example. Okay. We will do one or two examples, then you can get this idea very clearly. You will get this idea very clearly. Okay. So this is our identity. Okay, and we are now going to use it. Okay, so gradually we will speak about the properties and the important factors related with this Z transform. Okay, so I will take one example from your note. Okay, okay, so you can see that here you have the equation. Okay, here you have the equation. Okay, so we will see. Okay, so let's do this question. Okay, uh, let's try to find this question. I think I can copy it. See, yeah, I can copy. Mm, it is not completely copied. No? Okay, I will. Okay, so we have a signal xn. Okay, so it is 125701. 125701. 125701. Okay. So this is our series, and I think this is the zeroth sample. No? Is the zeroth sample. Okay. So so this is the uh, finite time series. Okay. This is a finite time series. You can see it, okay, because we have finite time samples are there. Okay, we have finite samples here. Okay, we have finite samples here. So it is a finite time series. Okay, so let's try to find the Z transform of this finite time series. Okay, so I think you can do it by yourself, but I will do it. Okay. So first, it is better to draw the sampled signal. Okay. Okay. So this is with respect to n, and we have xn. Okay. And this is 0. Okay. So we have 0 sample, and this is -1, and this is -2. This is +1, 2, 3, 4. Okay. So we have -1, -2 samples, and we have 1, 2, 3, 4 samples. No? So we have this 7 sample, 1, 2, 3, 4, 5, 6, 7. So we have 7 sample. Okay, and 0 is a 5. Okay, so it is 5. Okay, and the first sample is 7. Okay, so it is 7. Okay, it is 7. And the second sample is 0. Okay, no sample. Okay, and 6 and sorry, third and fourth samples are 1, 1. Okay, so it has 1, 1. Okay, and here you have 2, -1, 2, and -2 you have again 1. Okay, okay, this is 2. Okay. So this is our time series. Okay, correct. Now we have to, so now you can see it is in time domain. Now we have to convert this signal into Z domain, XZ. Okay, so we have to perform this Z transform. Okay, uh, so XZ is equal to n minus infinity to plus infinity xn z minus n. So this is our general formula. Okay, so in this case we have this n from -2 to 4. Correct. This n range is -2 to 4. Okay, so this n referred the number of sample. Okay, so this n referred the sample number, not number of sample. Okay, it is a sample number. Okay, so this n is referred to sample number. Okay, so here we have only 1, 2, 3, 4, 5, 6, 7 sample, and that sample is from -2 to 4. Correct. So in this case we have n from -2 to +4. Okay, -2 to +4, and we have xn. Okay, is at -n. Okay, so let us expand this expression. Okay, so you have n equal to -2. Okay, so x -2 is at the n, the sample number. It is -2 here. So here -2. Okay, so you will get +2 here. Okay, plus. Okay, so this is a summation. Okay, so this is a summation. Okay, so it is a plus, again plus. So we have x -1 z. So now n is -1. No? N is -1. So n is -1. So here -1. Correct. So you will get +1. Okay. and you have x0, z, now n is 0, so you have z0, okay, plus you have x1, z minus 1, plus x2, z minus 2, plus x3, z minus 3, plus x4, z minus 4. Okay, so you will get this kind of series, no? This kind of series. So now what you have to do is, okay, so you know the sample point. So you know the value of the samples, no? So you know the value of the sample. What you have to do is you have to substitute this value. Okay, then you can find the xz. Okay, capital xz is a transform signal. So let me substitute. So minus 2 is 1. Okay, so 1, and we have z minus 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 2, that means z plus 2. Okay, plus x minus 1 is 2. Okay, it is 2, and we have z minus 1, z minus minus 1, so we have z1. Okay, plus x0 is 5, and z0 is 1, no? So here you have only 5. Okay, x1 is 7, and 7 z minus 1, plus x2 is 0, so 0 z minus 2, so you will have 0 here. Okay, so we no need to write the 0 here. Okay, and x3 we have 1. Okay, so we have 1 z minus 3, plus x4 also 1, so you have 1 z minus 4. Okay, so this is our z transformation. So this is our z transformation. Okay, this is our z transformation. Okay, so what you can see here, what you can observe here. So one thing you can observe here is this is a power series, no? So this z has a power. Okay, z has a power, and you have a sum of that power terms. Okay, so we call this power series. Okay, so this is a power series. Okay, actually speaking, this is a finite power series. Okay, this is a finite power series. Okay, okay, so this is the z transfer. Okay, now we have a problem. Okay, it is not a problem actually. Okay, we have to concern another thing also. Okay, so what is this z? What is this z? Z is, as in Laplace transform, z is a complex value. Okay, z is a complex value. Okay, so actually we transform our time domain signal into complex domain. Okay, complex domain. We can also see the z transform like this, no? Okay, I hope you can understand what I am telling. Okay, so if you are not clear, you can stop me and ask question at any time. Okay, or you can send your question through chat box. Okay, so if you are not clear, you can ask the question. Okay, okay, so try to get the idea. Okay, after refer the lecture note, I think you can get a complete idea. Okay, so this is a complex value. Okay, complex variable. Okay, so we can denote this complex variable like this, no? This is we called Cartesian form or something, no? Cartesian representation for complex number, no? Okay, and also this z also can be represented in a polar form. Okay, so it will be like this, aj omega. Okay, so this is in polar form. Okay, I think you know how this conversion is done. Okay, Cartesian to polar or polar to Cartesian. Okay. Uh, so anyway, this is a complex variable. Okay, so you can see that uh, this this complex variable will have, so you know that complex number have imaginary parts and real parts. Okay, so this is imaginary of x, imaginary of z, and this is, sorry, this is the real of z. No? This is the real z. Okay, real z, and this is the imaginary z. Okay, okay. So this z can be any value here. No? So it can be 0, 1, 2, 3 up to infinity. It may be -1, -2, -3 up to infinity. Okay, it can be it can be a real number, complete real number, and it can be it maybe can be a, it can be a complex number, pure complex number, pure imaginary number. Okay, uh, one uh, 1i, 2i, 3i, so on. Okay, or -1i, -2i, -3i, so on up to minus infinity, and also up to plus infinity. And that z can have real part and also imaginary parts. Okay, so this z can be this kind of any value. Okay, so all this plane is valid for z. No, okay, so you can see that all this area is relevant to z. Okay, z can be any value within this area. Okay, did you get it? So we call this complex plane. No, can you remember that? This is we called complex plane. Okay, this is a complex plane. Okay, actually I think now you may have a sense that why we are transform this time to z transform. Okay, we can see that now we are dealing with some algebraic things. No, okay, okay, so that is one advantage of one use of z transform. Okay, we can convert an equation to a algebraic form. Okay, so gradually we will get that idea. Okay, okay, still you may wonder that why we are needing this kind of several transformation for analyzing. Okay, but you can see when we are uh, continuing, you can see that uh, this transformation will simplify our analysis and design. Okay, so we will see it gradually. Okay, so anyway, what is this? This is a complex plan. Okay, so I will again write this. Okay, okay, so this is our real z, and this is our imaginary z. Okay, so this z can be any value with this complex plane. Okay, this can be any value. Okay, so here it is up to my plus infinity and minus infinity. Here it up to plus infinity and minus infinity. So in this area, okay, z can be any value in this area. Okay, so we can see that sometime for some z value, for some z value, for some z value, okay, value, this xz or z transform or this power series. This is a power series. Okay, this is a power series. Okay, so this power series will get infinite value, infinite value. or sometime uh, the value we can't define. Okay, sometime undefined value. Okay, undefined value. Undefined value. Okay, most probably it will be infinite value, and sometimes we also get some undefined value. Okay, undefined value means you know that 0 by 0, this is not defined. We can't define this kind of value, and infinity by infinity, this kind of value is also not defined in maths. Okay, okay, so these are undefined value. Okay, so sometimes we get undefined value, or sometimes we get infinite value. Infinite value means the value we will get infinite. Okay, so and for some z value, okay, for some z value, this xz will get the finite value, finite mathematical value. This 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 power series will get a finite value. Okay, we can see that 1, 2, 3, 4, 5, 1.2, root 2, maybe. Okay, any rational or irrational number we can get. Okay, okay. So if if this power series get a finite value for some z value, we call this power series is converge. Power series is converge. Okay, converge to some value. Converge to some value. Okay, it is limited. Converge means limited to a value. Okay, and for some value, this x is can be infinite or undefined value. So at that time, we call this the series is not converge to a value. Okay, not converge to a value. Okay, so this is a very important concept. So you have to understand this. Okay, we will see when we are doing some exercises. You can understand this again. Okay, so anyway, uh, if for some z value, if you get a finite value, the series is converge. Okay, okay. So if not, the series is not converge. Okay, okay. So so okay, so we will see this this example. So we have this series. Okay, we have this series xz. Okay, we have xz. Okay, now xz I can write like this. Okay, z square plus 2z plus 5 2 by z plus 1 by z z to the power 3 plus 1 by z to the power 4. So, so we have 1, 2, 3, 4, 5, 6 because one term is 0. Okay, so we have only 6 terms here. Okay, so this is a finite power series. Okay, so you can see that. Okay, if you consider z is equal to 0, what happens? If the z is equal to 0, okay, that means here, if z is here, z is 0, you can see that this z can get 0 value also, okay? Any value in this square. So z will get this 0 value also. Okay, so if the z is 0, what is the value of xz? Can someone tell me what is the value of xz if the z is 0? Please tell me. Please tell me. Please tell me quickly. I think you can. Yeah. Yeah, yeah, I got one correct answer and another wrong answer also I get. That is okay, okay. That is okay. So anyway, thanks for your answer. Okay. So here you can see that happen. Okay, so I think you can see my screen now. Okay. So let's substitute and see what happened. Okay. So here z 0, 0 is square, you will get 0. Here also 0, you will get 0, and here you will get 5. Okay. Here you will get 5. Okay. 5 plus. Okay, but you have to uh, you have to you have to get account these terms also, but this terms will get the value. So if you get 2 by z, that means 2 by 0 here, and here also you will get 1 by 0, and here you also get 1 by 0. What is the value? If you divide some number by 0, what is the value? It is infinity. Okay, so this is infinity. Okay, so I think this is defined actually. Any number is divided by 0, it is defined. Okay, so I think it's expert. Okay, but how I understand this like this. Okay, this is not relevant with this is a transform. Okay, so you can ask maths teacher if you want more details. Okay, what how I think this, I assume this 0 is very small number. This is very small number, very small number. Okay, and infinity is very large number, very large number. Okay, very large number. Okay, so let's say that infinity divided by infinity. So here it is very large number. Let's say that that large number is 2 by there is 10,000 of zeros. Okay, and this another value is 1 by 10,000 zeros. So you will get here 2. Okay, if this is 3 by 10,000, it is also infinity, then you will get 3 here. Okay, so you can't give an exact value for this. We can't see that this can be a very small number, this can be a very low number, very small number, or it can be a finite number like 2 3 4. So this is not defined. Okay, likewise, if you consider 0 divided by 0, this is very small number. Let's say it is 2.2 by 10 to the power minus 10,000 0. That means 0.000 10,000 0 2. Okay, here it is 1 by 10 to the power minus 10,000 value. So you will get here 2. Okay, so it can be a finite. And if you see that if this is 100,000, here you will get 200. No? I'm not sure. Use a calculator and see. Okay. So here also you can see that this, if you divide this small number by small number, it can be a very small number. It can be a very big number, or it can be a finite number. So this also we can't define. Okay. And if you divide a very small number by very large number, definitely it will be 0. Okay, so 2 3 4,000 1,000 1 lakhs 10 lakhs 10 million trillion, also very small numbers with respect to this infinity, because it is very large. Okay, so you will get very small number. So if you divide any value by infinity, you will get 0. Okay, in the same way, if you divide any value by very small number, so definitely that will be a very small value now. Okay, so it will be infinity. Okay, so this is how I understand this concept. Okay, so I think you can use the same method if you are if you get confused. Okay, so this is not related with the Z transform. Okay, so for more details you can ask your maths teacher to help you. Okay. So this will be infinity. Okay, so this will be infinity. These are infinity. So if you have infinity, infinity, infinity at 5, so again you will get infinity. Okay, so this at z is equal to 0, this x z will get infinity value. So when the z is equal to 0, this x z is not converged. Okay, this is not converged. Okay, so in the same way, okay, tell me what happens if z is equal to infinity. In the same way, tell me what if z is equal to infinity. Okay, what happens? In the same way, if this z is, yeah, I got one answer here. Correct answer. No, yeah, I got the wrong answer as well as correct answers also. Okay. Anyway, thank you for your answers. Okay. So we will see. Okay, we will see. Okay. We will see when z is equal to infinity. What happened to this x z? Okay. So we have to, what we have to do? We have to substitute this infinity to this power series. Okay, so you have infinity square, so z now is infinity, so you have infinity square plus 2 infinity, okay, plus 5 plus 2 divided by infinity plus 1 divided by infinity to the power 3 and 1 divided by infinity to power 4. Okay, so this will be, so this very small number is divided by very large number, so definitely you will get very small number. Here also you will get very small number, and here also you will get very small number equal to 0. Okay, but these are infinity. Okay, so you can see that infinity plus 5, again you will get infinity. Okay, so the z, when z is equal to infinity, also x z is not converged. Okay, not converged. Okay, so you can see that except z is 0 and z is equal to infinity, all for all other values, this x z will be converged. Converged. Okay. So that set of value, okay, of z, okay, that converge means that get finite value, finite value, finite value for this x z. Okay, x z, we call that region of convergence, region of convergence. Okay, so this is very important concept. Okay, region of convergence, we call this ROC. I think in Laplace transform also you have find the ROC, region of convergence. Okay, so here also the same concept is there. Okay, set of value of z that x z will be converged to some value, that is the region of convergence. Okay, ROC. Okay, did you get that point? This is a note. Okay, here it is defined. This, the region of convergence of x z is a set of value of z which x z attain a finite value. Understand? All right. Did you get it? So this is the ROC, region of convergence. Okay, please highlight this and please remember this. Okay, so for a different transform, so you can see that when you convert any time series uh, into a Z transform, it will become a power series. Okay, it will become a power series, and uh, and we have to find this ROC depend on that power series. So different power series will have different ROC. Okay, so we have to find and we have to analyze what is the ROC for that specific power series. Did you get this? Okay, so let's do another example quickly. Okay, so let's do this one, the first one. Okay, so I think you can do this by yourself. Okay, please do by yourself, and once you finish, please raise your hand. Okay, then I will start. So here we have sorry, here we are given signal. Okay, sample signal, that is 1 2 3 4 6 or something. Okay, let's say that this is the zeroth sample. Let's say this is the zeroth sample. Okay, and can you find the Z transform, Z transform, and the ROC? Okay, so tell me the ROC. If you can put in the ROC. No need to put the Z transform. So once you calculate the Z transform, try to find the ROC here. Okay, and tell me what is the ROC for this power series, for this time series. Okay, so this is not a power series. Okay, you can see this is not a power series. Once we convert this to a Z transform, it will become a power series. Okay. Okay. So can you please get 5 minutes and try to find the ROC for this power series. Please try to find. Anyone got the answer? I think it is not very difficult. Okay, it is easy. It is same as like this. Okay. So I think we have to do a lot of things here. Okay. Still we are at the beginning. Okay. So get another three. Yeah, get the answer. Uh, maybe. Okay, we will see. Okay. This actually I also don't have idea. Okay. We will see after doing the problem. Okay. So one student has sent me a has sent me a answer. Okay. I got answer from one student. What about others? This is our example two. This is example two. I will wait another 2 minutes, around 2 minutes. Okay. Actually, once you understand this concept, it is easy to continue. Okay, because I think this is the first time you are learning the set transform. Okay, so maybe you will face some problem. You will face difficulties. Okay. Okay, someone also has sent me a power series also, the related power series. One mistake is there. It is not simple xn. That should be capital XZ. Okay. So maybe in the example, if you done this kind of mistake, you will get some marks reduced. Okay. Yes. Okay. That is okay. But please try to don't do that kind of mistake in exam. Okay. Here it is okay. Okay, so I will do this. Okay, we will see what happened. We will see the answers are correct or not. Okay, so other also please try to do with me. Okay, then you can get the idea. Okay, so we have to convert this signal. So this is a time domain signal because this n is related with time. Okay, so I refer this as a time domain signal. Don't get confused. Okay, this is a sampled signal. Okay, this is a sampled signal. If you send a continuous time signal uh, through a sampler, okay, through a sampler, you will get a discrete time signal. Okay, so this number of sample we normally denote using not number of sample number. We denote using n. Okay. Okay, so we will try to do this. Okay, so I will draw this sampled sequence. Okay, sampled sequence. Okay, so this is our sequence, sample sequence. So if I draw this, okay, so this is n, and this is, let's say this is x2n. Okay, so this is x2n. Okay, and we have zeroth sample, one, one, two, three, four, five samples. Okay, including zero. So we have 0, 1, 2, 3, 4. These 5 samples we have, and zeroth sample is 1. Okay, zeroth sample is 1, and the second sample is 2. Okay, that is we call first. If this is 0, this is first sample, so it is 2. Okay, and third sample is 3. The second sample is 3, and the third sample will be 4. and fourth sample will be 6. Okay, so this is 1, 2, 3, 4, 6. Correct? Okay, so now you have to find the Fourier transform. No, not Fourier transform, is a transform. Okay, let's take x is equal. Okay, so we have here, we have now, we have n, not from infinity, minus infinity to plus infinity. So this is also finite sequence. Okay, so you can see that this is also finite sequence. Okay, this is also a finite sequence. You have only 1, 2, 3, 4, 5 samples. 1, 2, 3, 4, 5 samples. Okay, so these are also impulse, no? These are also impulse. Okay, so we have only 5 impulse. Okay, we have only 5 impulse. Okay, so normally a discrete time signal, I think in MATLAB session we have learned this thing. Okay, so better to keep remember this thing. Discrete time signal we can represent as a collection of impulse. Okay, but this is not a practical situation. Okay, because in practically we can't achieve an impulse, because for an impulse this time period is 0, but we can't achieve 0 time within 0 time period. Okay, we can't achieve this 0 time period. Okay, so it may be a very small time period, but it is not equal to 0. So practically we can't achieve impulse. Okay, okay, so this is an impulse. Okay, so we have only impulse from 0 to 4. So n is from 0 to 4. We have this impulse xn is at minus n. Okay, so if I expand this, I have x0 is at 0 plus x1 is at minus 1 because this is minus n. X2 is at minus 2. X3 is at minus 3. X4 is at minus 4. So this is my series. Okay, so this is a power series, no? Because you have different powers for this Z. This complex variable, you have different powers. So this is a power series. Okay, so this is x0 is 1 and z0 is 1. So we will have 1 here. Okay, so x1 is 3. Okay, x1 is 2. Sorry, this is 2. Okay, this is 3. X1 is 2 and z minus 1. So you have 2 divided by z plus here x2 is 3 divided by z square. Because this is minus square, I get this down. Okay, so it will become plus. Okay, so these are, is that called Darshaka? Okay, I think you have that knowledge. Okay, I think you have that knowledge. Okay, so it says 3 is x2 is x2 is 3 by z square. X3 is 4 by z to the power 3 plus x4 is 6 by z4. Okay. So this is the xz. Okay, so this is our xz. That means is a transformed signal. So we have convert this xn. Okay, we have convert our xn into this z domain. Okay, so now we have to find the ROC. So how to find the ROC? So you can see that this kind of finite signals, okay, the ROC mainly will be depend on two values, 0 and infinity. Okay, so sometimes 0 will not include in ROC, or infinity not include in ROC. Okay, so what is the ROC here? Okay, so let me say that if Z is equal to 0, what is the XZ value? Tell me someone. If Z is equal to 0, what is the XZ value? Yes, yes, infinity. Okay, so XZ will be infinity. Okay, so this X this will be infinity because you have 2 by 0, 3 by 0, 4 by 0, 6 by 0. So all these term will get infinity, infinity, infinity. So XZ you will get infinity. Understand? Okay, so I didn't write the terms here. I directly write the answer. Okay, so I hope this understand. Okay. So you can see that when Z is equal to 0, okay, Z is equal to 0, the XZ will not converge, will not converge. Okay, so this Z is equal to 0 is not in ROC. Okay, it is not in region of convergence. Okay, this Z is equal to 0 is not in ROC. Correct? Okay, now see, when Z is equal to infinity, what happened? What is the value of XZ? Tell me someone. What is the value of XZ? Very good. What answer from one student only, and I hope if other student can also give me a wrong answer also, I am happy. Okay, because then you can make your mistake, you can correct your mistake. Okay, if you are making the mistake, you can correct them. If you are not doing if you are not doing anything, you will not make mistake. Okay, and you will not get correct them also. Okay? So try to do this. Maybe uh, your answer may be wrong, but after that you can correct it. Okay, but if you are not doing anything, then you will not get any mistake. But okay, so what is the exercise? Okay, uh, I will show you. So I'm going to apply this z is equal to infinity. Okay, so here if I substitute, you have 2 divided by z, 3 divided by, sorry, 2 divided by infinity, 3 divided by z square, that means infinity square, that means again infinity, and 4 infinity 3, infinity to the power 3. Okay, so it is again infinity, and 6 you have infinity. So you can see that this term will be 0, this term will be 0, this term will be 0, and this term will be 0, and you will get that x is equal to 1. Okay, correct. Okay, so anyway, the form of your answer is wrong. Okay, so you have mentioned that one of his one mentioned that ROC is between 1 and 0. Okay, 0 and 1. Okay, this representation is not correct. Okay, I will tell you why. Okay, so here it means that between 0 and 1 you have the ROC. Okay, if you write this ROC like this, ROC between 1 and 0, between 1 and 0, that means, okay, if you if we consider the z plane, okay, complex plane, so this is the complex plane. Okay, so this is real z and this is imaginary z. Okay, if you tell that the ROC not between 0 and 1, you see that ROC is only between this. Okay, between this, in z plane, only between this value in ROC. Okay, it is not correct. Did you get it? Mutushan, did you get it? Okay, thank you. Okay, so you can see that if you are making mistake, you can understand it very clearly. Okay. Okay, so we will see what is the ROC here. Okay, so you can see that if we write the, now you can see that the Z equal 0 is not in ROC. Okay, so here 0 is not in ROC, but Z, okay, tell me, Z in Z is equal to alpha, sorry, infinity. Infinity is in ROC or not? ROC or not? Tell me quickly. This infinity is in ROC or not? Is in ROC or not? Is this infinity is in region of convergence, or is this infinity not in region of convergence? Yes, very good. Actually, this infinity is in ROC, no? This infinity is in ROC. Yes, thank you. Yeah. So you can see that, okay. So you can see that when the Z is equal to infinity, xz will get the finite value, 1. If the Z is in infinity, this xz will get the finite value. It will get the 1. So that is a finite value. So definitely this infinity should be in ROC, no? Should be in this region. Okay. So infinity will in ROC, will be in ROC, but the 0 is not there. Okay. So if I draw the Z plane, okay, or complex plane, so this is the imaginary Z, sorry, real Z, and this is the imaginary Z. Okay. So you can see that except 0, except this point, except this point, all the plane is here, all the other values are in ROC, but the 0 is not in ROC. Okay, so this is not in ROC, this 0 is not in ROC, other all values are in ROC. Okay, did you get it? So I hope you get it. Okay, so I need another two. Okay, tell me, uh, find, okay, find the xz of delta n impulse. Okay, this is example 3. Quickly find this example 3. Find the xz of xn and ROC also. Quickly find. Actually, I hope to discuss the z transform properties and also in pole zero plotting. Okay, but I think we don't have much time. Okay, definitely I will do a recording and upload. Okay, if I couldn't complete that part today, I hope we couldn't complete. Okay, today I plan to do this region of convergent concept, and we have to do some properties. Okay, we have to do some properties of Z transform, that is time shifting property and time reversal property, uh, linearity property, convolution property. This kind of, there are around 5 or 6 properties are there. Okay, and also we have to know about the pole zero plot, pole zero plot of the Z transform sequence. Okay, So I hope we couldn't do that part. Okay. So anyway, we will try to do. Okay. So anyway, we will do because to get the idea, we have to do some exercise. Okay. Otherwise, you will not get idea. Okay. So please find this. Take 3 minutes and try to find the ROC of this impulse impulse. So it is very easy actually. Try to find it. Okay, I will do this. Okay. Okay, I will do this. Uh, so I think this is very easy. Okay, maybe you have you already know how to do. Okay, so impulse is like this. No, this is the delta n. Okay, so here n is equal to 0. Okay, yes, we will see. Okay, all the plan. Yeah, I hope that is for all the plan. Okay, so this is n. Okay, this is n 0. Okay, so so. Uh, So this is 1, no? That n is equal to 1. So this is delta n. Okay, so this is delta n. Okay, so if you find x is okay, of delta n, so now n is equal to 0 to 0, no? Only n is 0. Okay, so you have only one term, n is equal to 0. Delta n is at minus n. Okay, so delta n is equal to so 1. Okay, at z is 0 in 0. So you have z 0. Okay, so this is the z transform. This is the z transform. Z 0. Correct? Okay. Only one impulse. Okay. Here we have 3 or 5 impulse. No? In this case, we have 3 or 5 impulse. But here only one impulse we have considered. Okay, so it is the z naught, that means 1. Okay, so what is the ROC? What is the ROC? If you think, if you see that z is equal to 0, okay, z is equal to 0, very, if you consider a very small value, and if you get the 0 uh, 0 power, the value is equal to 1. Okay, and if z is very big value, okay, we don't care. Okay, it can be any very large value, but if you get the 0 power, it is again 1. Okay, so you can see that z is 0, this z naught will converge to 1, and if the z is infinity, also xz will converge to 1 again. Okay, and if you get any value for z, okay, the xz will converge to 1 for any value of z. Okay, xz will limit to 1. Okay, so you can see that if you consider this plane, complex plane or z plane, sometimes we call this z plane. Okay, or sometimes we called it complex plane. Okay, if you consider this complex plane, okay, so you can see that uh, any value within this z plane can be taken, can can be taken, uh, any value of this z plane is in ROC. No, it is in ROC. For any value of this xn, xz will have a converge value, finite value. Okay, so every values are in ROC. Okay, so any z value, okay, or all z values are in ROC. Okay, so this is the answer. Okay, so now we will discuss another one example quickly. Okay, so these are finite power series. Sorry, these are finite sequence. Okay, let's see. Sometime we will have infinite sequence also. No, so you can see these are finite finite sequences. Okay, because we have only finite samples there. Okay, for in first case we have 7 sample, in second case we have 5 sample, as I can 4 sample, as I can remember, 4 or 5 sample, and in our third example we have only 1 sample. So we have 5 we have 7 5 1 samples, that means all are finite samples. Okay, so all these are finite sequence. Okay, so all these are finite sequence. Okay, all these are finite sequence. These are finite sequence. Okay. Now we will see infinite sequence. Okay. Infinite sequence. What is the most basic infinite sequence? Can someone tell me? What is the most basic? We don't need to tell most. What is the basic infinite sequence? What is the basic infinite sequence? Can anyone remember? That is unit step function. No? That is unit step function, discrete time unit step function. That is our basic infinite sequence sequence. No, okay. So can you try to find? Okay, so this is somewhat hard. Okay, this is somewhat hard, but please take 2 or 3 minutes. So this will be our example 4. Okay, try to get 3 or 4 minutes to the find the z transform of this unit step function, discrete unit step function, and ROC. Try to find this. Take 1 or 2 minutes. Not you can't do it within 1 or 2 minutes. Take about 3 minutes and try to do it. Find the set transform of un. So this un is an infinite sequence, okay? Because we have infinite number of impulse. This is an infinite sequence. Okay. This is an infinite sequence. So I think in your now you can see that finite when we take a finite sequence, okay, when we take a finite sequence, when we get the Z transform, it is a finite power series. It is a finite power series. Okay. So if we get the infinite sequence, if we get the infinite time sequence, infinite time sequence, it will be infinite power series, infinite power series. So I think if we are when we are talking about infinite power series, what is the words come to your mind? If it is an infinite power series, whose name comes to your mind? This Taylor, no? Can you remember the Taylor series? Okay, so infinite power series, we can write in a compact form using Taylor's expansion. No? We can write it in a compact form. Okay. Okay, we will do this. Okay. So I think you maybe not remember that. Okay, we will see. Okay. Okay, we will see. Okay. So we will try to do this. Okay. So if you draw the unit step function, if you draw the unit step function, okay, un, okay. So how it comes? So we have this kind of impulse, no? This kind of infinite number of impulse. So this impulse goes up to infinity, plus infinity. Okay, up to plus infinity. So this is our unit step function, discrete unit step function. Okay, this is discrete unit step function, and this is our zeroth sample 1, 2, 3, 4, 5, 6, so on up to minus infinity. So we have infinite samples. No? Infinite samples. So this is an infinite sequence. Okay, this is an infinite sequence because we have infinite sample. Okay, so now let's estimate the Z transform of this UN. Okay, so if I get the Zn, okay, now n should be from 0 to plus infinity, not minus infinity to plus infinity, no? Because minus infinity to 0, it is 0. No any impulse there. Okay, from minus infinity to 0, no any impulse there, all are 0. Okay, so from 0 to infinity, we have infinite number of equal sequence, equal impulse. Okay, equally weighted impulse. So n is equal to 0 to plus infinity. We have this impulse. Let me take un z minus u. So you have if you have it is called, if you expand this, you will get u0 z0 plus u1 z minus 1 u2 z minus 3 u4 u3 u1 u2 z minus 2 u3 z minus 3 u4 z minus 4, so on up to infinity. Okay. So you will get infinite number of terms. Okay. So this u0, u1, u2, u3, u4, all are ones, no? Because this is not a weighted unity step function. So here the value is 1. Okay. So this is the unity step function, discrete time unity step function. Okay. So if you are not remember, please refer your note. Okay. I think in signal and system you have learned this concept. Okay. So we have z naught is 1, and we have 1 by z plus 1 by z square plus 1 by z3, 1 by z4, 1 by z5, z to the power 5. Okay. So on up to infinity. Okay. So you can see that this is also a power series. This is also a power series. This is also power series. I think this is also called geometric power series. No, these are I'm not sure. Okay, because I am not good at that this serious things. Okay. Okay. So as I can remember, this kind of power series we call geometric power series, because here we have finite difference between two terms. Okay, all terms. First term is multiplied by the other terms. No? Then you will get the, if you multiply the previous term with 1 by z, you will get the next term. Okay. For example, if you multiply 1 by z square by 1 by z, then you can get the 1 by z square next term. Okay. So if you have finite difference between these two, I think it is, we call this also power series. Okay, I'm not sure. You can refer your note. Okay, or you can refer the internet. Okay. Okay. So this kind of one we have. This kind of one we have. Now this is a power series, infinite power series, and sometime we may have we may have chance to find a compact form, compact form using Taylor, or sometimes we call Maclaurin or something. No, Maclaurin series or something. I'm not that was one. Okay. So anyway, using the Taylor expansion, you will get you can try to find the compact version for this power series. Okay. So you can Google it. Okay. You can Google it. Taylor series. Series. Taylor series. Let's see. I think you can Google this very easily. Okay, so you can get. I think this one. No, this one is the related power series. So it is given by 1 by x z. No, okay. So you can see that if we have, okay, if we have 1 by x by x square by x 7 by x 4 x 5, so on, we can write this as 1 by 1 minus x. Okay, and for all x, this series not satisfied. Okay, so there are some condition for this x. Okay, so I think x should be the the absolute value of x should be less than 1. Okay, so if you are not comfortable, you can Google. Okay. Okay, try to read these things. I think there is the condition is there. I think in our textbook also the condition is there. So I will use that one. Okay, so this one. Okay, uh, the, the absolute a should be less than 1. Okay, so this is one of Taylor series expansion. Okay, one of Taylor series expansion. We can use that one. Okay, here it is not mentioned as Taylor series, but it is included in Taylor series or Maclaurin series. Okay, so if I go to the journals, okay, so this is x2 should be less than 1. Okay, x2 should be less than 1. Okay, so this is the uh, power series, compact version of the power series we can use for our case. Okay, so I use this one directly here. Okay, so X is that I think for your exam you no need to remember this power series. Okay, but you should have an idea. Okay, sometime power, if we have an infinite power series, not all power series, we can't say that all power series. Okay, but many power series we can have a compact form in using this Taylor's method. Okay, Taylor series or Maclaurin series. Okay, so keep that idea. Okay, but in your exam, I hope if you want to apply this kind of series, it will be given. Okay, it will be given to the exam, so you no need to keep remember all these things. Okay, don't worry, don't no, you no need to keep remember, but you have to know how to apply them. Okay, so that is the requirement. Okay, uh, so here you have xz. Okay, and you have so you can see that this so I can write this like this: 1 plus 1 by z 1, 1 by z 2, 1 by z 3, so on I can write. No, okay, so on I can write. Okay, so if any student couldn't understand this step, you can ask me. Okay, because these sometimes these are very basic mathematics uh, things. Okay, so I skip sometime I skip the step. Okay, so if you have any doubt, you can ask me. Okay, if you are not remember, if you are not familiar with this, you can ask. Okay, okay, but I think you are familiar with these things. Okay, okay, so here it is 1 by z this square, z1, 1 by z this square, 1 by z that, so on. Okay, so I can write this as 1 1 by 1 minus x, that means 1 minus 1 z, like this. Okay, so this is my x z. Okay, so this is my x z. So you can see another advantage we can get from z transform. What is that? Okay, so here you have an infinite series. Here you have an infinite sequence. Infinite sequence. But now, when you convert that infinite sequence into Z transform, okay, you have a compact version. Okay, compact expression or closed form expression. Closed form expression. No? We can say this as a closed form expression. Okay. So you can see that here for this power series, okay, we can't have a closed form expression. The UN is not a closed form expression. Okay, this term is not a closed form expression. That is a uh, that is the representation. Okay, so by UN we denote this kind of sequence, infinite sequence. Okay, it is not a closed form expression. Okay, but here you have a closed form expression. Wait a minute. Closed form expression. One by Z apron. Okay. Okay. So this is a closed form expression. Okay. So that is one advantage of converting a time series uh, into uh, into a Z transform. Okay, Z domain, time series into Z domain. Okay, so if you want to find the ROC, you have to use this condition. Okay, because if this condition not satisfied, this power series will not exist. Okay, if this condition is not satisfied, this power serial will not exist. Okay, so you have to use this condition also to calculate the ROC. Okay, so now you can see that okay, x absolute value of x should be less than 1. Okay, should be less than 1. That means here x is identical to 1 by z. So that means 1 by z absolute value is equal to 1. Okay, so if you get the cross product, okay, you can see that the absolute value of z will be greater than 1. Okay, absolute value of z will be greater than 1. So if you draw the ROC in the Z plane, so this is the real Z plane and this is imaginary Z line. Okay, so this is the Z plane or complex plane. Okay, so what is absolute value of 1? Absolute value of 1. The absolute value means the magnitude, no? So magnitude should be greater than 1. So if you find this kind of circle, okay, so within this circle, if this is 1, if it is a unit circle, okay, because it is 1, we call this a unit circle. Okay, if it is a unit circle, you can see that, okay, you can see that you can see that uh, so this is the absolute this region is the this boundary is equal to absolute value is equal to 1. Okay, okay, because absolute value in complex variable in complex domain, the absolute value is the magnitude, only the magnitude. Okay, okay, so if you find the absolute value, it will if the z is x by iy, if you find the absolute value, you will get x square by y square root. So this is the absolute value, z absolute. Okay, so if it is 1, if it is 1, okay, if it is 1, if it is 1, this is not this is not a unit circle, no? Okay, this is not a unit circle. I think I wrong. Okay, I will draw it again. Okay, So you can see that ROC should be greater than 1. The absolute value of Z should be greater than 1. Okay. So absolute value means the magnitude. Okay. So magnitude means the radius. No? The radius, the magnitude is this thing. So it should be the, yeah, it should be, yeah, it should be the, it should be this range. Okay, it should be this range, and this value is R. Okay, this value is R, and it should be 1. Okay, it should be 1, and here is also it should be 1. Okay, so this if you convert this to the polar form, this if you find this theta, okay, so this is R cos R square cos square theta plus R square sin square theta. Okay, and if you get the square root, that means if you find the magnitude, you will get R square square, that means R. Okay, so so this should be the unit circle actually. So the ROC should be greater than 1. So ROC will be out of this range. No? So this this dark area is the ROC, region of convergence, for this case. Okay, for unit step function. Okay, did you get it? Did you get this? Or do you have any confusion? Okay, please try to understand. Okay. Yeah. Yeah, absolute value may be without considering minus or 1. No? Okay. So if you have minus or 1, okay, if you get the absolute value, you will get this. Okay. So I think this is also related with this one. No? Okay. In complex, if it is a complex one, if you get the absolute value, it is not only the value. It should be the magnitude. Okay. Example. Okay. One example. If you get Z is equal to I 1. Okay. So if you get the so let's take, so this is Z. Okay. So if you consider this Z minus or plus, okay, if you get Z minus or plus absolute value, it should be, you said that this is Z and it is equal to X plus IY. This is not correct. This is wrong. Okay, this is wrong. Okay, this is wrong. I think that is your idea. No? That is what you are asking. Okay, this is wrong. I think you can verify with your mathematics teacher. Okay, mathematics one, mathematics lecture. Okay, if you want to get more details, so this is wrong actually, because when we are saying magnitude, okay, when we are saying magnitude, that is the uh, that is the uh, how can I say, that is විශාලත්වය, magnitude නතමානේ. So that is the magnitude of this complex number. Okay. Okay. So it come x square plus y square square root. Okay. And it will be a plus value. It will be a plus value. So because a magnitude should be a plus value. Okay. So this is the value. Okay. But if you consider real value, okay, that means this imaginary part is 0. Okay, this imaginary part is 0. Okay, if you get the real value, this imaginary part is 0. So you will have is x only here. Okay, so if you have z is equal to x, if you get plus or minus z, that means plus or minus x. Okay, And if you get the absolute value here, plus or minus absolute value, that is x square plus 0 square root, and you will get x. Okay. So here the plus and minus sign is cancelled. Okay. But here also we have to calculate magnitude here. Magnitude means the value without considering the plus or minus. Okay. Vishalatto. Okay. So I hope you get it. Did you get it? That is how I can explain this. Okay. So here it denote this Z. When you say that Z absolute Z means this is complex variable. So always this referred to the magnitude. Okay. Always this refers to the magnitude, not the plus or minus value. Okay. Did you get it? I think we are running out of time. Okay. So we will stop here. Actually, I plan to complete this Fourier, this a transform property. Okay, this a transform properties, and also pole zero plot. Okay, pole zero plot. So we have to. These properties are very. You can see that these properties are very important when we are analyzing the system, especially LTI system. Okay, and this pole zero plot is also somewhat important. Uh, I think you already know that using pole zero plot, we are finding the stability. Find the stability of the system, no? Stability of the system. Okay, when you are learning Laplace transform, I think you have learned this concept. Okay, okay, and so using pole zero plot, also we can get idea about the stability of a discrete time system. Discrete time system. Okay, we can see it by observing the location of poles and zero. Okay, so I will try to record these two parts and upload it. Okay, and upload it. Okay. Uh, So I think if you have time, I think now you can have a basic knowledge to go through that note. Okay. Now I think you have basic knowledge to go through that note. Okay. So please try to go through this. Okay. Try to understand what are the things here. Okay. So we have done several examples. Okay. And try to do these examples by yourself. Okay. And also there are some concept with the ROC. Okay, sometimes you may not understand this stuff. Okay, this ROC stuff, it is okay. Okay, I will explain it later. Okay, gradually we will try to understand these things. Okay, and uh, try to do some exercise by yourself. Okay, so I will wind up because now already assignment 1. Okay, I will try. Okay, I will try. Actually, that assignment is not prepared by me. Okay, it is prepared by Dr. Udesh. Okay, so if you if I upload if you want to if you want me to upload the sample answers, I have to do the assignment by myself. Okay, so actually this I have a time issue also. Okay. So anyway, I will try. Okay, I will try to do that one. Okay. Anyway, anyway, I think we will have a tutorial session, okay, before the exam. Okay, uh, I think you have around 2 or 3 weeks. No? I think next month, the end of next month, your end examination will begin. No? I don't know exactly. So before that, we will try to do 1 or 2 tutorial, and we will try to solve some uh, difficult question in those assignment. Okay. Okay, we will try to do something. And shall we wind up now? Do you have any problem? I will be here around 1 or 2 minutes. Okay. So if you have any doubts, you can ask. Okay.